Hi, I'm Chris from LearnGrasshopper.com, and today I have something really special. Demo lesson called Computational Thinking Process. This lesson is part of a Grasshopper Fundamentals training. In this particular video, I will show you why computational thinking is one of the biggest superpowers of future engineers. Why is this set of skills needed to convert real-life challenges into tasks that can be solved with help of a computer? I will show you why this mindset is fundamental to almost every engineering task. Below this video, you can find a link to the presentation in the PDF format. This PDF is for free and you can just download it without giving any email. This lesson is one of the first lessons from my comprehensive Grasshopper training, where I'm taking a user with zero programming experience and going step by step through 13 well-structured modules with more than 300 practical exercises. This training is the first step to becoming an engineer for zero with skills that allow automating time-consuming work and taking design to the next level. Worth to mention that advanced users will learn from this training a lot as well. On grasshopperfundamentals.com, you can sign up for the next edition of this online training and reserve your seat. You will land on my mailing list, which already consists of more than 6,000 engineers, and I will let you know when the next edition starts and come back to you with the best offer. That's all, and let's go to lesson. Now we'll talk about computational thinking. You're most likely familiar with the term computer programming. In just the last 3 decades, this comparatively new and fast-evolving field has gained enormous popularity, and now we can see even young children starting to write their own scripts and programs. If you start that early, it is natural to choose computer science as a course of a study. With such qualification, you may even apply to your dream tech company, be it Google, Facebook, Microsoft, Apple, or any other. Computers are able to do a wide range of amazing things, from basic laptops capable of simple word processing and spreadsheet functions to incredible complex supercomputers completing millions of financial transactions a day. It would be accurate to say that computers control the infrastructure that makes modern life possible. Nevertheless, the truth is that computers themselves are actually stupid. Despite all of this incredible stuff that they can achieve, in reality they are useless without a programmer. They need a human-given command and inputs in order to perform computation and to produce meaningful output. Without a programmer, computers will not know how to behave. Stuart Welch put it into a nice words. Computers are incredibly fast, accurate, and stupid. Human beings are incredibly slow, inaccurate, and brilliant. Together they are powerful beyond imagination. Computer programming is about connecting humans and computers. Although there are many different programming languages and many different types of computers in existence, the important first step is the need to have the solution in mind at a conceptual level. Without an algorithm, there can be no program. Computers, in contrast to humans, are very efficient at the task because they are happy to keep executing the same instructions over and over and over again without ever getting bored. As I mentioned earlier, computers can be used to help us solve problems. However, we need to understand a problem itself before it can be tackled and solved. Computational thinking is the step that comes before programming, which allows us to understand the problem. And this is a whole point of computational thinking. It allows us to take a complex problem, understand what the problem actually is and how it can be solved, and then develop possible solutions. In the end, we can then present these solutions in a way that a computer, a human, or even both, are able to understand it. There are 4 key techniques and steps to computational thinking. Let's start with the first one, which is decomposition. So decomposition means that we are breaking down the complex problem or system into smaller, more manageable parts. Decomposition can be defined as a process of solving a complex problems and breaking it into more sub-problems that can be solved much easier. Solving a complex problems may get difficult sometimes, but finding the solution for every sub-problem will be simple, after which the sub-problems can be put together for finding the full solution to the original problem. The second key and part of computational thinking is pattern recognition. So here we are looking for similarities among and within problems. Allow us to skip having to consider every individual concept and rather use previous experience and methods to efficiently and simultaneously deal with multiple objects and come up with a reusable solution. Third one, it's maybe will be hard to understand and something new because it's an abstraction. Here in this aspect, we're focusing on the important information, only ignoring irrelevant detail. Abstraction allows us to create a general idea of what the problem is and how to solve it. The process instructs us to remove all specific details and any patterns that will not help us resolve our problems. And the last one, here we are going to create our algorithm. So developing a step-by-step solution to the problem or the rules to follow to solve the problem. It automates the problem-solving process by creating a series of systematic logical steps that process a defined set of inputs and produce a defined set of outputs based on this. Each step is as important as the others. Together, these form that layers of the foundation for programming. Remember that only be applying for them all together. Will you be able to achieve the results if you consider them all together? Omitting any of them will make your foundation really weak. So remember, we are coming back to this 4 key aspects many times in this course. To visual computational thinking, I will present all steps in a practical example using all these 4 keys. So let's say we have a plan to finish a marathon in under 4 hours. The world record for the marathon is about 2 hours, so 4 hours may not sound like a challenge. However, it is not an easy thing to do. So you will have a lot of preparation to do unless you have already been training regularly for several years. So let's assume in this example that you are not experienced marathon runner. So to cross our desired marathon's finish line, let's apply computational thinking. Here is again this 4 aspects that I present you. At the first glance, we don't know how to easily solve this task. Just thinking of running over 41 kilometers at once can be overwhelming and seem near to impossible to do. That's why we have to break this complex problem down into a series of small, more manageable problems. If you remember, this is a decomposition. In our case, we have to create a training plan. Training has to be divided into smaller distances. You're not going to run the full marathon in your training. All planning has to be done several months before the actual marathon starts. Great, the first step is completed. You have a training plan described in the smaller steps. Now, each of these smaller problems needs to be looked at individually, considering how you may have solved similar problems previously. So here we talk about pattern recognition. Maybe you have participated in competition before. Maybe the running route is similar to what you have done before, but just with the scaled down distance of 10 kilometers. This step is about finding similar problems. Not all solutions you may have used before can necessarily be applied. So this was about pattern recognition. The third step now have to focus only on important details while ignoring irrelevant information, which is called abstraction. This one is easy. We have to focus on regular training and healthy and balanced diet, good sleep, and perhaps avoiding unhealthy things like cigarettes and alcohol. So this is about abstraction. So this is about prioritizing. The final step, lastly, we need to create a simple step to solve each of the smaller problems. To do this, we have to design the rules that can be designed and easy to follow, an algorithm. In this metaphor, we would have to instruct a program, ourselves, in a way to perform all planned training. So for example, set the alarm clock to 6 a.m., wake up in the morning, dress in comfortable clothes, warm up your muscles, begin interval training 8 times 1 kilometers, do stretches afterwards, have a regular scheduled diet eating and right balance of carbohydrates and proteins, go to work, sleep and repeat. This is everything about algorithm, like programming ourselves to do all these small tasks that we spoke before. So finally, the simple steps or rules are used to program a computer to help solve complex problems in the best way. The planning and preparation part is like computational thinking, and following the training assumption is like programming. Hope that this example clearly explains how computational thinking can be applied in real life. If we look closer to application of it, we'll see that every engineer needs to use computational thinking on a daily basis. If we think about it, these 4 foundations layers are very similar to what we are already doing as architects or engineers. In our day-to-day life, what we do is abstract problems so they can be solved. Additionally, we are very good at doing analysis and evaluating solutions. Scheme of work for an engineer. First of all, decomposing the huge structure into parts. So beams, roof structure, columns, and so on. Second, identifying which parameters drive the structure. Third, pattern recognition, considering how similar structure have we been built previously. And 4, defining the underlying logic of a structure and developing a solution to the design or the rules to follow to solve the design. However, the last step has traditionally been replaced with manual labor in one way or another. Of course, we have software that aids us in this process, but we are often at the behest of a huge software companies and software silos. Let's say we have a problem that we want to automate. If this is not possible in the software that we at the given time have access to, we need to file a wish item to the developers. And it may take everything from a couple of months to 5 years to get access to this functionality. This, of course, among others, lead us to do it manually instead because we must get it done now. That leads us to the point where we have to add functionality to the programs or create them from scratch by ourselves. And as I said before, this process is called algorithm creation. Here is a question. What is an algorithm? Simply put, an algorithm is a step-by-step procedure. In math and computer science, algorithms are used for calculation or problem solving. Still, the concept can be seen elsewhere in places like recipes, games, or even instruction for assembling things like furniture, IKEA. Algorithms are defined by lists of consecutive but not necessarily sequential steps, each with well-defined instructions. Algorithms have beginning and ends. We can say that this is like a list. In their beginning states, algorithms take data in the form of variable input. Inputs are processed through the algorithm steps and transform into some kind of information or output that is given in the end state. Algorithms exist in many different forms, from written instruction to flowchart to formal computer language to electrical circuits, just to name a few. Let's take a look at this algorithm. Here, our job is to go from home to our office. And for that, we have created an algorithm in a form of a flow chart. So first of all, the first step, beginning of the algorithm, we need to of course leave our home. Afterwards, we check the time. And here we have something that divides in the two action, depends what time is. So if it's before 7 a.m., so we are going to take a car. If not, we are taking a bus to reach our work. And now we are going to step by step an algorithm. So it's of course just a simple example, just showing just how many steps we are going to do and which part in this algorithm we are going to choose. To sum up, computational thinking is not a tool nor programming. It's not even thinking like a computer, as computers do not and cannot think. They are not that smart, to say it in a really nice way. Simply put, computational thinking is a process for solving complex problems. Programming tells a computer what to do and how to do it. As Steve Jobs said once time, programming teaches you how to think. This means you attack the problem in an entirely new way. You always look for the logic behind the problem and what is driving what. To do that, we have to speak with computers in the same language, and about that I will tell you more in the next video. So at the end I have a book recommendation for those who would like to explore more computational thinking by the Meet Press Essential Knowledge series. Author is Peter Denning and Matti Tedre. So for those who would like to explore more and go to the next level of computational thinking. So here is a link where you can just buy your book. So that was all for this lesson. Mark this lesson as a complete and see you in the next video where we're going to talk about programming. If you like this video and you think it's practical, please give it a thumb up. If you know someone who should take the first step to becoming an engineer for zero, please share it. Maybe this video will change the mindset of working for someone. Now I invite you to grasshopperfundamentals.com where you can register for the next edition and get the best offer. Thanks and see you on the learning platform. Have a good one.